So in this short video we're going to look at halogenoalkanes and the environment. We're going to be considering chlorofluorocarbons, often referred to as CFCs. And these compounds have got lots and lots of applications in society, particularly in fridges and solvents, things like for dry cleaning. They're very useful because they've got a very low reactivity, so they don't react with the other chemicals in those products, and they're not toxic, so they're not dangerous to humans. But unfortunately they do lead to an unexpected problem. They lead to the depletion of the ozone layer. Now the ozone layer is in the upper atmosphere. The ozone layer is protecting us from harmful UV radiation. Now the ozone layer in the upper atmosphere forms when oxygen atoms react with oxygen molecules. See if you can write an equation for the reaction of oxygen atoms with oxygen molecules. If you've had a go at that, you should have got an equation something like this. Oxygen atoms, O, react with oxygen molecules, O2, to form ozone, O3. Now, ozone is, like I said, very beneficial to us because it absorbs UV radiation, and that UV radiation can cause skin cancer, so we don't want it to come through the atmosphere and affect us. So how do CFCs affect the ozone in the atmosphere? So scientists discovered that the ozone up in the upper atmosphere was broken down by chlorine radicals. So where did the chlorine radicals come from? Well, CFCs are compounds that contain chlorine, fluorine and carbon. So I'm going to draw an example. This is just one example of a CFC. I'm going to have 2 chlorines on my CFC and 2 fluorines. So it's a chlorofluorocarbon. And what happens is when UV light shines on our chlorofluorocarbon, the carbon-chlorine bond is broken. Now this is very, very similar to the reaction that we studied in alkanes, free radical substitution, where the bond is broken and radicals are formed. So we've formed a radical that is a chlorine radical. And it's this chlorine radical that causes all the problems. Just like in our alkanes pack, this mechanism is a free radical mechanism, and just like in the alkanes pack, when we break this bond, we are initiating the reaction. This is an initiation step. So those chlorine radicals go on to react with an ozone molecule and catalyse the breakdown. The chlorine radical react with the ozone molecule and grab an oxygen atom and leave us with an oxygen molecule. So a molecule plus a radical makes a molecule and a radical. The radical then moves forward to the next step, reacts with another ozone molecule, because that's what we've got in our ozone layer, just ozone molecules, and we're getting our chlorine radical back. So the reason that it catalyses the reaction is because chlorine radicals come in at the start but come back out at the end. They are regenerated. These 2 steps that have radicals at the beginning and radicals at the end are examples of propagation steps, because they propagate the reaction, keep it going. And we can see that chlorine is a catalyst. The chlorine radical is a catalyst. If we put those 2 equations together, and we can see that the radicals here and here, chlorine radical in, chlorine radical out, ClO radical formed, ClO radical used, are going to disappear, they're going to cancel out, and we're going to be left with 2 ozone molecules make 3 oxygen molecules. We have destroyed some ozone. Now we have to try to find a way to get around this problem. We've got to try and find some alternatives to CFCs. So we've been trying to find some compounds that do not contain chlorine that will be better for the environment. And some of the examples we come up with are HFCs. That stands for hydrofluorocarbons. fluorocarbon, so we've removed the chlorine element. An example might be CH2F2. We've now got no chlorine in our molecule. And this will limit the amount of destruction of the ozone layer. That's it for this little section. You can go review the whole of the halogenoalkanes pack now and make sure you're understanding completely everything that you need to know.